Good day and welcome to the latest in the Getech webinar series. This session we're going to look at some of the work we've been doing on mapping temperature with depth as part of GLOBE. So I'm Chris, I'm a geophysicist at Getech. And we'll just look at some of the logistics. So the webinar will last about 30 minutes. The video will be posted hopefully within about 2 days. And there'll be opportunity for Q&A at the end of the webinar if you stay around. If you want to ask a question, this is how you do it. If you click on the white on orange arrow, it will open the GoToWebinar control panel if it's not already open. And then under questions, you can type your question, but you must remember to send. If you don't press send, we won't receive it. So an integrated solution to mapping present day temperature with depth. And it's this integration that we're going to focus on really, because it's the use of different types of technique, which I think is particularly important in the work that we've been doing. So what are the controls on temperature at depth? Well, of course, we can measure surface heat flow, which essentially is measuring the temperature gradient close to the surface. And these are relatively shallow estimates, some very shallow from simple probe measurements, some rather deeper from wells, but they're all certainly at the top of the crust. And we're going to combine those with some geophysical constraints, particularly the Curie temperature depth. And this is something which affects magnetization, and so we can measure it with the magnetic field. And this is a rather deeper temperature marker. And then at the end, we need to integrate these because our main data sets are not available everywhere. And from that, we can generate a global thermal model. So temperature with depth, why is that useful? Who cares? Well, we've divided this into kind of two levels. It's kind of mapping. So here we're looking at maybe high level screening of basins for hydrocarbon prospectivity, and also, assessing geothermal resources. So the main resource for geothermal energy essentially is high temperature. And if we can map the temperatures within the Earth, we've got a good idea of where the resource is. We can also use the results in more analytical approaches. So we can use them as inputs to basin modeling. And of course, these are basin modeling through time, and our measurements are just the present day. And these will impact on our models of maturation history, thinking about hydrocarbons, in addition to the impact of temperature on things like cementation of reservoirs. And in a more general sense, having this integrated thermal model can help us interpolate between the points where we do have specific data, such as surface heat flow observations. So what is the Curie temperature depth? Essentially, it's the depth below which rocks become non-magnetic due to temperature. So any magnetic material, if you heat it up, it will reach a point, and so-called Curie point or Curie temperature, at which it essentially stops being magnetic, stops being able to maintain magnetization. And for magnetite, which is a dominant magnetic mineral within the crust, that is at about 580 degrees C. So we think of our simple model here. Here's the surface. We've got temperature increasing with depth. At the top here, we may have sediments, and sediments are not entirely non-magnetic, but in a relative sense, we can often consider them as non-magnetic. And then when we get to the magnetic basement, we encounter this magnetic layer. and magnetic layer will then continue until we get to the Curie isotherm. And once we go beyond the Curie isotherm, the rocks become non-magnetic again. So if we can map this surface, the bottom of this magnetic layer, that can provide us with information to produce a model of temperature with depth and how it varies laterally across the globe. So this is the workflow that we've basically followed. We've aimed to produce an integrated global Curie depth grid. And Curie temperature grid is something that we can produce directly from each of our data sets, from terrestrial magnetic data, satellite magnetic data, and from surface heat flow. All of these we can estimate the Curie temperature depth, produce an integrated Curie depth grid, and then from these we can back calculate, and we can calculate the heat flow through the crust, and we can also calculate the temperature through the crust and produce grids of temperature with depth. So thinking first about terrestrial magnetic data. And so terrestrial magnetic data, we mean data collected on an aircraft, on a ship, or maybe even ground data. So in this global compilation of Getech's magnetic data, there's very little ground data actually, but there's quite a lot of airborne and a certain amount of shipborne data. And these are integrated into a coherent data set, and we need big blocks of reasonably high resolution data in order to be able to estimate the Curie temperature depths. So here we see our simplified model again, and our observations are generally quite low altitude. And so the distance or the depth to the top of the magnetic layer and the bottom of the magnetic layer are significantly different in most cases. And so we stand a chance of resolving both the depth to the top and the depth to the bottom. And the way we do that is by looking at the power spectrum, the radially average power spectrum, or the log power spectrum of the magnetic data. And if we take this simple model here, where we've got the top and bottom at 2 and 10 kilometers, for a random magnetization, we have this black line here, the bottom of the lines. Now this part of the curve is quite straight, and from the slope of that part of the curve, we can estimate the depth to the top of the magnetic layer. And this is a method which is actually commonly used in geophysical analysis of interpreting magnetic data to estimate depth to basement. Now, if the magnetization continued forever, then this line would continue straight up to the axis here, where it gets to infinite wavelength. But because we're lacking magnetic material in this deeper section, and the deeper parts will generally give us longer wavelength parts of the magnetic field, we see that at the longer wavelengths, at the smaller wave numbers, the magnetic field power is reduced. And for this random model, we get a peak, and from the peak and the slope, or there are other ways of formulating that expression, we can estimate the depth both to the top and to the bottom. However, what we often see with radial average power spectra is that there isn't a peak, and they will often continue like this. And what we also observe, if we look at the actual distributions of magnetization that we see in the crust, is that it's not entirely random, and in fact it's more like a fractal distribution. And in a fractal distribution, the magnetization is correlated to a greater or lesser degree. And so beta here is our fractal index. Beta equals 1 is the purely random case. But as the fractal index increases, the peak reduces and in fact disappears, and we're left with these curves here. So the method we're going to use involves taking one of these curves and an estimate of the fractal index to regenerate the curve we would have if the magnetization was truly random. And from that, we can estimate the depths to the top and the bottom of the layer, and therefore the Curie temperature depths. So this is kind of working through an example. So here we have an area of magnetic data, and here we have a window, and we're going to look at a whole series of windows. And this window is about 200 kilometers across, and this is the log power spectrum we get from that window. And as we see there, there is no peak. But once we've applied this so-called diffractal operator, we end up with a different power spectrum, and now we do have a peak. It's a little bit noisy, but we have a peak in our power spectrum. And from here, we can do two things. We can use this part of the power spectrum, which is not quite the longest wavelength, to estimate the depth to the top of the magnetic layer. We've got a value here. We can actually redraw our power spectrum in a slightly different way. And then from this part of the power spectrum, which is pretty much the longest wavelength, we can use that slope to estimate the depth to the centroid. That's to say the depth to the middle of the magnetic layer. And once we've done that, we can produce a theoretical power spectrum and check how well it fits to our modified power spectrum here. And that will give us confidence that the fractal index is correct. Once we have the depth to the top and the centroid, of course, we can estimate the depth to the bottom. And we have a value then that we can plot on this grid here. And we can build up a map of the depth to the base of the magnetic layer or the Curie temperature depths. And this is how this method works. Interestingly, what we find is that the fractal index is quite heavily related to the geological regime. And so we can use Getech's crustal architecture layer to inform the values for the fractal index that we need to use. And what we find is that over shield areas, we generally have low values of fractal index. And so the magnetization is more or less random. Whereas in oceanic areas, we have higher values of fractal index. And that means that the magnetization is quite strongly correlated. And that's not a surprise because, as we know in oceanic areas, we have magnetic stripes, which give us quite a lot of coherency within our magnetization and our magnetic field. And so, we've assigned different values to different elements within our crustal architecture to give us appropriate values to use to estimate the Curie temperature depths from the terrestrial magnetic data. Looking at satellite magnetic data, this is a global model. This is the LCS1 model, a fairly recent model, and this includes some data from the SWARM mission. The SWARM mission is currently flying. It's actually a collection of 3 satellites measuring the magnetic field. Because the measurements are quite high, the resolution of the data is quite low, but the good thing is that the coverage is global and it's consistent on a global scale. So in the satellite case, our satellite is now a long way above the crust, 300 kilometers elevation or higher are all of the satellites. And therefore, we can't really expect to be able to resolve both the top and the bottom of the magnetic layer. And the magnetic layer within continental crust is generally somewhere in the lower crust. But what we can do is attempt to look at the amplitudes we get from the magnetic data to estimate the thickness of the magnetic layer. So again, for each point, we will take a window of data, and from that window of data, we can estimate the amplitude of the magnetic field, and that's what we see here. Generally, that will increase in areas where the crust is thicker and where the depth to the Curie isotherm is thicker, or the thickness of the magnetic layer is greater. And a simple approach, we can just multiply this by a factor, different factors we use for ocean and continent actually, and estimate the thickness of the magnetic layer. What we've done more recently is actually to estimate in regional terms the magnetization within the crust based on the terrestrial data. And so we've got now a more robust version of the Curie temperature depth from satellite magnetic data. And then Curie temperature depth from surface heat flow. So here again, we have our model. Temperature is increasing with depth, and therefore heat flows from deep to the surface. And so here we have the MOHO, and the heat flows from the mantle and impinges then on these crustal layers, which have different values of K, the thermal conductivity, and A, the radiogenic heat production. And in fact, we find that the heat flow increases as we go from the MOHO to the surface, such that in fact, about 40% overall of the surface heat flow is actually generated within the crust based on these A values and the radioactive decay of potassium, uranium, and thorium, which are by far the main radiogenic elements within the crust. And this is how we use that. So this is a geotherm, what a geotherm might look like. And this is the one-dimensional equation which governs that. So I say straight away that because we're working here on a global scale, everything we're doing at the moment is in one dimension. So we find that the temperature at depth will depend on the temperature at the surface. That's not a surprise. It will depend on Q0, the surface heat flow, and the conductivity. And so this slope here is defined by the heat flow and the conductivity. And at this point, we have a kink, and that is because the conductivity changes. So we're going here from sediments to basement, and in our model here, we have an increase in the thermal conductivity as we go into the basement. What we can also see is there's a slight curvature along this orange line, and that's due to this term in the equation and the radiogenic heat production. And so the radiogenic heat production causes these geotherms to curve. And the curvature doesn't look that great, but if you're projecting a long way down through the crust, it can have quite a big impact. And so basically what we do is we take our model of conductivity and heat production, our surface temperature and our heat flow, and we basically track down along this curve until we get to the Curie temperature. And then we read off the value, and that is our Curie temperature depth from surface heat flow. Now, it's not quite as straightforward as that. We can't just use a single equation for each of these layers, and that's because these parameters actually vary with depth. So thermal conductivity varies with temperature, and of course, temperature varies with depth. So what we find is at high temperature, great depth, conductivities tend to become more similar. They converge to around 1.85 watts per meter per Kelvin. The heat production also will generally change with depth. So within the upper crust, the empirical models show that it will generally decrease with depth. Once you go into the lower crust, it will be somewhat lower, and in the mantle, it will be very low. But still, we can apply these equations in an iterative way to estimate the Curie temperature depth. Again, we can use the crustal architecture to inform this process. And particularly here, we're using the crustal architecture to estimate what is an appropriate value for the heat production within the crystalline crust. And so what we find is that for different types of crust, we get different typical values, and we've done a fair amount of analysis looking at whole rock geochemistry and also airborne radiometric data to estimate the values that are appropriate for this part of the model. Once we have a global result, we need to assess its quality in different areas. So this is for the heat flow derived Curie depth, and based on the coverage, on the apparent reliability and consistency of the data, we can say that there are areas where we're very confident, where we have medium or relatively low confidence, or where there's very little heat flow data at all. And in those areas, we have to use the magnetic data sets. So here we have an area where we have all the different data sets. We find that they don't look the same. And in fact, one thing that doesn't look the same is the resolution. And we generally have higher resolution from the heat flow data, sort of moderate resolution from the terrestrial magnetic data, and lower resolution from the satellite magnetic data. But the good thing about the satellite magnetic data is we will have a value everywhere. And so we can always fill in with that. So we will end up with a final integrated grid, which is populated on a global basis. And once we have this integrated Curie temperature depth grid, what we can do is we can follow this curve in reverse. So using our model again, we can go from our Curie temperature depth up here, and we can thereby estimate temperatures at depth all through the crust, and we can also estimate the heat flow values if we wish. And here we have the temperature at a series of layers within the same area, generally increasing with depth, but at rather different rates in different places. So in summary, what we've done in our method, we've combined terrestrial magnetic data, satellite magnetic data, and surface heat flow to give us an integrated global Curie temperature depth. And then we've produced grids of temperature with depth, and we can use those for basin screening, basin modeling, geothermal resource analysis, etc. So just the mention of what we're going to look at next. So as well as developing the heat flow database, we're going to look at temperature of the upper mantle from gravity data, the lithosphere-asthenosphere boundary, which is another temperature marker, and trying to apply machine learning. And so there's a very brief illustration of some of those. Upper mantle density we've calculated from our global gravity model, global depth basement model, global MOHO model. And from this, we can estimate the mantle temperature, the upper mantle temperature. And here we've compared that with temperatures just below the MOHO that have been calculated by Schutt et al. From PN velocities from the US array. The lithosphere-asthenosphere boundary, it's a deeper temperature control point, about 1330 degrees C. We need to be careful only to use data that come from seismic data, but again, we can use these to interpolate temperatures in the crust. And in terms of machine learning, what we've tried to do is we've used a whole load of different parameters and tried to use them to predict the surface heat flow. And this is the sort of analysis you get, and you find that some of these data sets predict the surface heat flow really quite well, and some don't really help a lot. And then you need to be careful with your analysis and make sure you're only really picking things which are sensible and are not cyclical in some sense. So here's an example, heat flow data as control, and we can use that to build a method and predict surface heat flow over the whole area. It works well in a data-rich area. The question is going to be, the challenge is going to be, can we extend it to areas where we have fewer control points and fewer data prediction data sets? So that's where we're at. Do we have any questions?
Yeah, thanks, Chris. We do have a couple of questions. So first question is, what controls the resolution of different methods?
What controls the resolution of the different methods? So let me go to this slide here. So basically, if we're working with surface heat flow values, it's actually the distribution of the data. As long as they're reasonably consistent, that governs the resolution. There's a limit to the resolution if we're trying to predict the Curie depth, which is quite a long way down in the crust, but it's really to do with the number of data points. So if we only have a very few data points, if we only had 4 data points in this area, the most we could calculate was 4 depth values, and then we'd have to interpolate. The magnetic data depends on the window size that we use. We will often end up using about 200 kilometers, quite a big window, and that will limit the resolution. But the reason we need such a big window is that we need to have a window which is probably 5 or 6 times the depth that we're going to estimate to the Curie temperature depth. So in areas where the Curie depth is shallow, we might actually be able to use a smaller window and get better resolution. And the satellite magnetic data set is really just limited by the fact that the satellite is at quite a high elevation, and we're only imaging the longer wavelengths of the magnetic field. So the windows we use here are more like 700 kilometers. So quite broad.
Brilliant. So we've got a few other questions. So can you calibrate the temperature or heat flow to the real world temperature data?
Can we do that, or have we done that? I mean, we can do that, and we've done some tests. What we see is that in general we have a reasonably good correlation, but at smaller scales we don't always see correlations so directly, and partly that's due to the different resolutions of the methods and potentially the limitations of the data. And the thing with the surface heat flow observations particularly is that in their raw form, before we've made them compatible, there can be quite a lot of variation. But yes, that's certainly something that we could do, and we would be interested to do that.
So we've got oftentimes crustal architecture is defined by grav and mag data. So how do you resolve the double unknown in the equation?
The double unknown in the equation. Well, it's not really a double unknown because we're not using the magnetic data in the same way. When we use magnetic data to help us define crustal architecture, we're primarily thinking about the types of structures that we're imaging, and also in a general sense, the texture. And it's often the textures that we see in the magnetic data sets, and particularly in derivatives of the magnetic data sets, that we use to define the different areas on our crustal architecture maps, and also the same with gravity. Again, we're looking at building models, but again, we're looking at structures which are in the sort of relatively shallow crust, and again, we're also looking at textures, the type of signatures that we see, and those are both rather different from the more strictly numerical analysis that we're using to estimate the Curie temperatures from magnetic data, and also to estimate the upper mantle densities and therefore temperatures from the gravity data.
Okay, thank you. So we've got a few more questions. So what kind of machine learning techniques are you using to determine the best source of heat? What kind of accuracy are you getting?
Kind of machine learning techniques. I think we're using an algorithm which is called a random forest algorithm, which is implemented within ArcGIS Pro. So that is what we have been using. I mean, one of the aims of that sort of method is, that's where the random forest comes in. We use a whole ensemble of different collections of parameters to try and build up the model, and that's essentially to try and avoid overfitting of the model to the data. What sort of results do we get? From the top of my head, I think it's giving us what it says is about 65% prediction capability for the data that we don't put directly into the model. So basically, when you're building your model, you give it a subset of your data, generally quite a big subset of the data, and then you test how well you can predict the remainder of the data. And so far, that's at about 65%, which is pretty good. But as I said, that's in an area where we've got a lot of data of different types, and the challenge is going to be to achieve reasonable results with a lesser quality of data.
Thanks. I think it's also worth pointing out that the machine learning, we're at a very early stage in implementing this at the moment, so
yes,
we may be able to better response on that later on. I'm just going to do one more question, Chris, but we've got lots of other questions that have come in. For anybody who's sent in questions that we haven't answered, I'll get Chris to answer them all after this session, and send you all messages that will answer your questions. So just the last question for today, Chris. Does the effect of lateral heterogeneity in K, or lateral heat advection, make the 1D approximation a tiny bit wrong, or how much wrong?
It makes it at least a tiny bit wrong, and possibly very, very wrong, depending on on how much it varies. So at this global scale, we've done everything on a grid of 1/4 of a degree, so about 25 kilometers. And at that resolution, we cannot image things like individual salt domes, for example. And salt is quite an anomalous material, including in terms of its conductivity. But that's something that is beyond the scope of this model, and you would definitely want to work in more than one dimension, really 3 dimensions, if you're going to look at the things like salt domes, where you have really quite rapid lateral changes in conductivity. Over much of the area, though, looking at on a global scale, our knowledge of conductivity, is limited in its resolution, and so in terms of most of the area and working on a global scale, I would say that the 1D approximation is not of itself the limitation. It's the fact that we don't, have really good estimates of, all the physical parameters at a small scale to put into it.
Okay, thank you, Chris. As I said before, apologies to everybody who we've not been able to get to their questions, but I will get Chris to answer them after the session. Thank you, Chris, for your time, and thank you everyone for attending. There will be a recording of this made available, and you'll be sent a link as soon as that's up on the website. Please feel free to share the link amongst your colleagues. But if you've got any other questions, then email us directly and we will respond to those as soon as we can. But for now, thank you very much for your time, and thank you, Chris, for the presentation.
Well, and thank everyone for coming. Yes.